So I'm Kun Fang from the Chinese University of Hong Kong, Shenzhen. So the same university with Masahito Hayashi. So today's talk is about dynamic quantum circuit compilation, and this is the archive number. And this is a joint work with my collaborator Yilan Li from Wuhan University, and also two of my students, Ru Qi and Mo Lan. So currently we have like many challenges of quantum computing, right? So at least they come from two aspects. The first aspect is with my collaborator Yilan Li from Wuhan University, and also two of my students, Ru Qi and Mo Lan. So right here, the echoes from challenges of computing, right? So at least they come from two aspects. The first aspect is with my Okay, so the main challenges come from two aspects. The first one is the scalability issue, right? So because currently the quantum computers are very limited by the number of qubits that are available for doing our computation. So we really need to make efficient use of these qubits, this limited number of qubits when we design or executing our quantum algorithms. And another problem is the fidelity, right? So current generation or quantum computers in the near future are very easily affected by noises. So when we implement our algorithms, we need to do circuit optimization and also need to do quantum error correction to ensure that the results are correct. So previously, we have studied a lot about the static quantum circuit, so which is a kind of circuit, kind of standard quantum circuit that you prepare an initial quantum state, and then you implement sequentially a lot of gate operations on the initial state, and then you perform measurements at the very end. So this is called static quantum circuit. But due to the progress of quantum hardware, actually we can implement more general quantum circuit, which is called dynamic quantum circuits. So the main feature of this dynamic circuit is that it contains mid-circuit measurement and also reset operations. So mid-circuit measurement means that we can perform measurements in the middle of the circuit, and then we can make use of this measurement result to control the later circuit instructions. So for example, here if the measurement is 0, we do not implement this X state. If it's 1, we implement this X state. So the circuit itself is dynamic. And more importantly, once we measure the physical qubits in the middle, we can also reset. So this qubit is decoupled from the rest of the qubits. So we can reset this qubit and initialize it again to another quantum state, and we can make use of this physical qubit for subsequent operations. So this kind of circuit is called dynamic quantum circuit, and it's actually very nature in quantum error correction, because in error correction we need to do a syndrome measurement on part of the qubits, right? And then we can make use of this information to correct the later the other qubits. So this is a very nature notion in quantum error correction. So currently we have many kinds of physical platforms for doing quantum computing, and two of the mainstreams are superconducting quantum computers. In this kind of platform, it is relatively easy for scaling, but it has limited qubits connectivity and also very short coherence time. But for trap ion platform, it has very long coherence time and very nice qubit connectivity, but it is relatively hard for scaling up. So the dynamic circuit combination technique in this work mainly targets the platform like this. Okay, so we want to reduce qubits to the extreme, but this will also increase the depth of the circuit. But I guess for platform such as the trap iron quantum computers, it will be very suitable. Actually, they're a fast quantum circuit. So, for example, from from 2000, Nikon also supports the implementation of dynamic circuit on the trap iron system, and also Google, and then recently Atom Computing. This company has also supports the implementation of dynamic quantum circuit on the these neutral atom platforms. And also recently, there's also progress in Shenzhen, China, particularly suspect their hardware can also support the implementation of mid-circuit measurement and also reset operations. So dynamic circuit compilation will be very well motivated from the progress from on hardware side. So here, what we want to do is that we want to rewire a static quantum circuit into a dynamic circuit, right? But we hope that once we do the rewiring or the compilation, the dynamic circuit we have is equivalent to the previous one, which means they yield the same sampling results. No matter what kind of input you give me, we will always have the same results, so they're equivalent. But the good thing for dynamic circuit is that it will require fewer qubits for its implementation. So here is a favorite toy example. So here we have a quantum circuit with two qubits, right? But we can easily see that we can rewiring the second line to the first line. That is, we postpone all of the circuit instructions on the second qubit until we finish the instructions on the first qubit. And then the right-hand side will become a dynamic circuit. We implement the initialization on the first qubit. We apply the Hartman gate. We do the measurements. And once this measurement is done, we reset this physical qubit to Q1, and we apply the Hartman gate and to measurement. So this is a dynamic circuit, and it only requires one physical qubit for its implementation. Right? So here's a slightly more complicated example that requires 3 qubits, but we can also postpone the instructions in this part to a bit later, and then we can rewire all the instructions on the third qubit and also the second qubit to the first and second one, like this. So once we do this kind of compilation, the resulting circuit only requires 2 qubits for its implement. So yes, we can also have a even more complicated example, but this one is a bit hard to observe its compilation by manually. So, but indeed it can be rewired into a dynamic circuit that only requires 3 qubits. Okay, but such a kind of compilation is not easy by just observing the structure of the circuit. So if we have a even larger quantum circuit, it will be very hard to compile this manually by hand, right? So automatic tools is definitely needed here. So that is what we do in this work. So the main message of this talk is that we hope to make use of the tech to address the issue in practice. So there's a large gap between the theoretical quantum algorithms that we want to implement, which requires a lot of physical qubits, but in practice we have a quantum sources. So we hope to make use of this compilation technique to address the gap here. Okay. And of course, that besides the saving, there are also other byproduct benefits. So when we do the uh, compilation, we will see the circuit itself consider mapping the logical circuit to the quantum hardware. We will require less swap gates. This has to when we implement the compile circuit. This is the byproduct. Okay. And that worth mentioning is that the complementary to other position or circuit mapping, but the techniques here can integrate it with the existing ones. Okay. So next, so now we move on to talk about the details, how we do the circuit compilation. So before that, we will make use of different kinds of quantum circuit notations. Okay, so the first one is circuit diagram, which most of people are very familiar with. And this diagram can be equivalent to a circuit instruction list. That is, we make a list of the all of the circuit instructions sequentially by the time that each of instructions is implemented. So these two are exactly equivalent. And when doing compilation, the most important thing here is not about the type of the instructions. What more important is the dependency of the circuit instruction to the others. For example, here the circuit instruction with ID6 needs to be implemented after the instruction 3 and instruction 4. So this information matters. So with this, we can abstract our circuit diagram to a graph, which is directed acyclic graph named DAG. So for each circuit instruction in the original diagram, we abstract it to a node in our graph. And if and each of the edges in the graph will correspond to the dependency of the circuit diagram. For example, as I just said, the instruction 6 need to implement after 3 and 4. So we have an edge here pointing from 3 to 6 and from 4 to 6. So this directed edge represent that the instruction 3 need to be implemented before 6. Okay, this is kind of dependency that we need. And we can divide all of the nodes in the DAG into 3 groups. Right? The first one is which we call the root vertices. That corresponds to the vertices with 0 integrity. It also corresponds to the initialization operations in the circuit diagram. And we also have the terminal vertices, which is the vertices with 0 out degree, and it corresponds to the measurement in the original circuit. And the rest of the nodes will be called the internal vertices. Okay. So sometimes when we do the compilation, the intermediate nodes are not important as well. So what matters is the connectivity between the root vertex and the terminal vertex. So we will further simplify the DAG representation as a simplified DAG. So here we keep all the root vertex and the terminal vertex, and we add edges between them. So depending on the reachability of between these nodes. So for example, here, if we consider the root vertex 0 and the terminal vertex 10, if there's a path, directed path in this graph, right? If this path exists, then we can add a directed edge in this simplified DAG from 0 to 10. Okay, so this helps simplify the computation a lot. when we do compilation later. Okay, what really matters here is the reachability or the connectivity between the root vertex and the terminal vertex. Okay, once you do this, the simplified DAG will be actually a bipartite graph. Okay, so when do computation, we can also characterize a bipartite graph with a matrix. So we know that for any uh, G, we can write it as a, so for example, if there's edge between Vi and Vj in the original graph, then we will assign the element Aij in the matrix as one. Otherwise, it will assign zero. So this is called adjacency matrix of the graph. And particularly for bipartite graph like this, the adjacency matrix will look like this. It has a very unique structure. So only the right upper corner here is non-zero. So this non-zero part is called bi-adjacency matrix of this bipartite graph, and it contains all the information in the simplified DAG. So there's a very useful lemma here that if you have a directed graph which is acyclic, this is equivalent to say that its adjacency matrix is nilpotent. Okay, this is a useful lemma that will be used later. Okay, with all of these notions of circuit representations, now we can start our circuit compilation. So the first step is to compile our static quantum circuits into a graph. So I still use the same example as before. So we have a 3-qubit quantum circuit like this, and we postpone part of the circuit instruction a bit later, and then we rewire this part and obtain the dynamic circuit. So if you look at the corresponding behavior of the DAG graph, you'll see that the DAG graph of this original circuit is look like this here, and the DAG in the final circuit looks like this. So you can see that when you do the circuit compilation, it's essentially do some operations in the graph, which means you add a new edge from the terminal 8 to the root 2. That's all you need. So now we can see that if you want to do dynamic quantum circuit compilation, it's essentially to add edges in the DAG graph. But you can you hope to add as many edges as you want. This will help you to reduce the number of qubits later. But there's also some constraints when you add in the edges. So the first constraint is that you can only edge from the terminal vertex to the root vertex. And the second condition says that you can only, so for each of the terminal vertex, it can only add one new edge. And also for each of the root vertex, it can also be connected with edge. Okay. And so once you add the new edges, you still want to this edge, hope this graph to a good graph. Okay, so these are the 3 constraints that you need when you're trying to add new edges to the DAG. So of course, all of the implementations can be implemented on the simplified DAG as well. So okay, so once we add the new edges to the graph, we can go to the next step from that we make use of the new graph and extract the information from the graph to compile our circuits. So this is the last step, and we will introduce the intermediate step later. Okay. So once we have the new edge from 8 to 2, then we can make use of the topological ordering of this graph to define the feasible execution sequence of all the instructions. And then we make use of the new sequence of instructions and do a kind of operations called qubit reallocation. So we to obtain the dynamic circuit instructions, and this is equivalent to obtain the dynamic circuit that we want. So qubit reallocation here, for example here, so because we are adding a new edge from 8 to 2, which means we will make use of we will implement the instruction 2 after the instruction 8, and we make use of the qubit on instruction 8, which is qubit 1, to implement the instruction that was originally assigned to qubit 2, which means here we reallocate all of the qubit registers 2 to qubit register 1, 0 here. Okay. So this is about the qubit reallocation. So the whole compilation procedures will look like this. So you have a static quantum circuit, you obtain its equivalent circuit instruction list, and you extract its instruction list as a DAG representation, and also based on the connectivity of this between the root and the terminal vertices, you obtain the simplified DAG, and you are trying to add edges to the simplified DAG. And once you add your edges, you can do the qubit reallocation, and you can compile your dynamic circuits. So this is the complete workflow. Okay. So it's worth mentioning that sometimes the circuit may have some commutable structures. In this case, for example, all of the CZ gates are commutable, right? So in this case, when we build our DAG, we will not impose any dependency in our DAG graph. This will leave us more flexibility to do the compilation later. So for example, if we impose the dependency on the left-hand side, you'll see we can only add one new edge. But if you ignore this dependency, you can add more edges. Okay. And such a commutable structure actually are very common in quantum applications. For example, in the QoA quantum circuit, we have the ZZ gates are all commutable, and also in IQP circuits, the intermediate instructions are all commutable with each other. Okay, so now we go to the core part. So how can we determine? So before we do the compilation, so how can we determine if a quantum circuit can be compiled at all, right? So here we call a quantum circuit is reducible if it can be compiled to a quantum circuit with fewer qubits, and otherwise we will call it irreducible. So here you can see that if we want to add one more edge in the simplified DAG, it cannot be a complete graph, right? So this will give us a proposition like this. So if a static is reducible, which means it's irreducible, which means we cannot compile it further if and only if the simplified grid is complete by confined that we mentioned earlier. Actually, it's roughly like this, and here M is the number of instructions, and N is the number of qubits in the original circuit. So of course, we have some other criteria to determine whether a circuit can be compiled or not. Okay, but I will skip it here. Okay, so how can we do the optimal quantum circuit compilation, right? So still in the same example here, for every quantum circuit we can obtain a simplified DAG, and this will correspond to a bi-adjacency matrix B. And then we can introduce another matrix based on the bi-adjacency matrix in this like this, and we call this matrix as the candidate matrix. So actually, the candidate matrix represents that all of the candidate edges that you can add without violating the previous constraints. So for example, here, if we use the variable Fij as the indicating whether you add a new edge from terminal I to root j, then you will see that all of the choice of your feasible solutions F will essentially be a submatrix of this candidate matrix. So in this case, our edge is from A to 2, which means we choose the variable Fi here as 1. And this is the submatrix of your candidate matrix of the optimal circuit compilation. So since Fij indicates the edges, the new edges that you want to add to the graph, and we add as many edges as possible. So we need to maximize the summation of all the edges, and we need to make sure that the new edges satisfies the discrete constraints on the left, right? So we can translate all of these constraints as a more mathematical formulation, and for each of the constraints, we will introduce a few constraints in the programming. So the optimal compilation can be precisely characterized by this binary integer program. So the variable here is Fij that is chosen from 0 or 1, indicating whether you add this new edge or not. Okay. So solving this problem exactly is very hard. So there's a follow-up work later prove that this program is actually NP hard in general. Okay, so despite the NP hardness, we can still make use of the circuit structures to analyze some of the important examples. So here we have analyzed many of the important examples, well-known ones in the binary integer programming, and we can actually found that their optimal compilation schemes for them. So for each of the red block here, which means we found the optimal compilations, and for each of the blue block here, it indicates that the circuit itself is not reducible. Okay, it cannot be compiled further. Okay, so for example, there's this Deutsch-Jozsa algorithm. If the oracle is implemented like this, then we can find this candidate matrix, and we select a submatrix from the candidate matrix like this, and we can argue that this is essentially the optimal choice in your programming. And also for global algorithm, if because the diffusion operator make use of the multiple control gauge, and you can easily argue that this will gives you an irreducible circuit. Okay, and we want to mention that our compilation only depends on the specific circuit implementation. So for example, for the grower algorithm, we may not use this multiple control gauge, and that there may exist some circuit decomposition for it, and for that one, it might be compilable. Okay, so because solving the optimal solution is NP hard in general, so we also devise several heuristic algorithms to add as many edges as possible for our compilation. So the one of the most important one is the greedy algorithms. So the idea is that we hope to make locally optimal choice for each iteration steps. Okay, this will help us to maximize the possibility to add more edges in the subsequent steps. So the procedure is like this. So for the greedy algorithm, we temporarily consider to integrate one edge into the simplified DAG, and then we update the candidate matrix, and we score the candidate matrix by the summation of all elements in the matrix. This will tell us how large the room are left to add more edges. And once this is done, we have the score matrix. We randomly select a candidate edge with the highest score. Okay. So this is the rough idea. So for example, if we have a 5-qubit BV algorithm, and if we want to evaluate the importance of these newly edges, then we can imagine that we already integrate this edge in the graph, and once this is done, we can update our candidate matrix based on the 3 constraints that we need. And once this update is done, we count how many ones in this matrix, which means here we have 3 ones, so we give the score of this edge as 3, and we can do the same thing for all the other candidate edges. Okay, and we obtain this score matrix. We pick one of the edges from with the highest score, and it's very important that we choose this randomly if we have multiple edges with the same highest score. So this because this randomness will help us to avoid the dependency of the circuit relabeling, and it will give us better performance in practice. Okay, so the worst case time complexity for our greedy algorithm is looks like this. So it's polynomial algorithm, and M here is the number of circuit instructions, and N here is the number of qubit in your original quantum circuit. So we have also tested our heuristic algorithm in a lot of examples. For example, here we test our algorithms to the quantum circuits that used to claim quantum supremacy, and here we introduce the reducibility factor, which indicates how well our algorithm performs. So the larger the value, the better. So here you can see that it's very interesting that all these 3 quantum circuits used to claim the quantum supremacy, that happens to be irreducible quantum circuit. So if you reduce the cycles of this quantum circuit, you'll see that they will become reducible. So this tells us that when we design quantum circuits for to show quantum supremacy, there's a trade-off between the circuit depth and the structure complexity of the circuit itself. We want to make the circuit to be as complex as possible, so that it's hard to simulate classically, but we cannot make it arbitrarily complex because we have the limitation from the hardware, right? So there's a trade-off, and it happens that all of these 3 circuits are just becomes irreducible quantum circuit. And another interesting fact is that we noticed that the supremacy circuits used by Sycamore 53 is actually compilable. You can reduce this circuit by 1, and this coincide with the history that the Sycamore 53 this chip has 1 physical qubit that does not work very well. So when Google designed their quantum circuits, they do not make use of this physical qubit. So this breaks the symmetry or the complexity of the circuits they design. We have also implemented our algorithms for QAOA circuits and compare it with another paper, which is named DCKF here. So the smaller value, the better. Okay, so it's very clear that our methods performs much better than the previous best known results. Okay, because the reason is that when we design our algorithms, we take account of the commutable structures of the QAOA circuit. We have also implemented the algorithm for random quantum circuits and compare it with the DCKF paper, and it's very clear that our algorithms outperforms the original algorithms in most of the cases, and particularly for this ratio, R is larger. The R is the ratio between the number of gates divided by the number of qubits. Okay. And also, particularly for random IQP circuit, our algorithms outperforms almost for every cases. And finally, we have also implemented our algorithms for a particular example, and we compile our circuits and we do noisy simulation of these circuits by using the parameters, the hardware parameters provided in this paper. And we will see that when we compile the circuits, we reduce the number of qubits, and as a byproduct, the circuit becomes more compact. So it helps us to choose the physical qubit with better performance. So this will help us to improve the fidelity when implement these circuits in hardware. Of course, we do this by numerical evaluation, and we hope that we can test this on the realistic hardware devices in the future. Okay, so this is a brief summary of this talk. So because we noticed that there's a gap between the theoretical quantum algorithms, which requires a lot of qubits, but in practice, our quantum computer are very limited with the qubit resources. So we hope to make use of this dynamic quantum circuit computation technique to address this issue. So it helps us to do qubit saving, and it also has a byproduct to make the circuit compact. So we need less swap gates when we do circuit mapping to the hardware, and this will help us to improve the fidelity when implement the circuit. Okay, so this is all about today's talk, and thank you very much for your attention. So you can refer to this archive paper for more details.
Thank you for the talk. Is there any question from Nagoya side? So can I ask a question?
Yes, please.
So I think there is some kind of trade-off between number of qubits you are saving and the, whole runtime of the algorithm. Yeah.
Yes.
And can you have a kind of quantitative trade-off, or it is just some kind of empirical trade-off?
Yes, this is kind of yes, empirical observations, but it matches our intuitions, right? So I guess yes, that's a very good question. So it would be nice to have a more analytical trade-off. So actually, we're trying to do this, but we don't get a very good result. So we increase the circuit depths, and we want to see if we increase the depths, how it behaves when we do the compilation. We have a result that if the depth of the circuits is not the depth, the number of gates is roughly like log n squared, something like that, then it's very likely that the circuit becomes irreducible. But we still have a bit of a problem in the rigorous proof. But yes, it's a very good question. If you can have a more analytical result to showing this trade-off, it will be very nice. Yes.
Thank you.
Yes.
Any question from like online audiences? If not, let's thank the speaker again.
Okay, thank you.
So the next talk will start in 10 minutes. Mr. DU, are you there? Okay, please share the screen. Hello, Mr. Liu. Could you turn on the camera and mic?
Hello everyone. Can
Thank you.
you see my screen?
Yeah. Okay. So let's
Hello?
start the next session. So the next speaker is Liu from the University of Hong Kong. And
Sorry, I can't hear you.
oh,
Hello?
can you hear me? Can you hear me?
Okay. It seems that audio works fine. Then I will start my presentation right now. Thank you for being here. In today's talk, I will be discussing how to use symmetries in quantum hardware to facilitate quantum circuit mapping. This is a joint work by Kunwang and me. So let's first consider a question. So can we implement this example quantum circuit using typical quantum hardware like IBM Falcon? This graph shows the qubit connectivity in IBM Falcon. So it can be easily see that this is impossible because this quantum circuit requires one qubit to be coupled to four other different qubits, right? But in IBM Falcon, each qubit is coupled to at most three other qubits. So, and if we want to implement this quantum circuit anyway on this quantum hardware, then will need to transform this circuit to an equivalent form. And this transformation is known as quantum circuit compilation. And during the compilation, we will need to select a group of qubits in the quantum hardware to implement this circuit, right? And this selection is known as qubit mapping. Well, so when doing qubit mapping, we should keep in mind that different qubits, even on a single quantum hardware, different qubits will have different gate errors and measurement errors, and we will need to select the best group of qubits to implement our quantum circuit. So here I have shown the benchmark result of gate error and measurement error for three typical IBM quantum systems. And you can see that the gate error ranges across one order of magnitude. So which means some quantum gates have higher fidelity than others. And this deviation, this variance is very significant. So we should take this into account when searching for the optimal circuit mapping. So, but how to implement this idea? How to take into account the impact of the variance in gate error? So last year, a group in IBM Quantum proposed a new process known as quantum circuit mapping. So that is, the idea is, so we can see that in a quantum hardware with qubit connectivity shown here, there are many repeated patterns, right? So if we have a quantum circuit that can be implemented on, for example, the first group of qubits, then it should be able to implement it on many other group of qubits because this group of qubits share the same connectivity, right? So in that case, what we can do is that we first we determine an initial circuit mapping. That is, we find a tentative group of qubits to implement our quantum circuit. And then we search for all the equivalent circuit mappings featuring the same qubit connectivity. And then we can estimate the circuit fidelity for these circuit mappings and find out the best circuit mappings that maximize the circuit fidelity. And this technique, this search and maximize the circuit fidelity technique is known as circuit remapping. So we can see that the circuit remapping technique involves solving a problem of searching for all the repeated patterns in a graph. And this problem is formulated as a subgraph matching problem. So that is, given a graph G and a graph T, what are all subgraphs in G that are isomorphic to T? We need to solve this problem if we want to implement the circuit remapping technique. However, 50 years ago, it has been proven that subgraph matching problem is NP time complete, which means it is difficult to solve in general. So our idea is we noticed that many practical quantum systems have highly symmetric structures, like this shown here. So can we use these symmetries to facilitate the subgraph matching process, and therefore the circuit remapping process? So in fact, it is possible. So here I will briefly explain how our symmetry-based circuit remapping process works. So we have a quantum circuit shown in the figure A that we want to implement on a quantum hardware, and the connectivity is shown in figure D. First, we need to transform the quantum circuit a bit to make it compatible with the connectivity of our quantum hardware, right? And that transformation results in the circuit in figure B. And what's important is that there are many group of qubits in the quantum hardware that can be used to implement this circuit shown in figure B. And we need to find out all these group of qubits and identify which one is the best. And that will goes to subgraph matching problem, right? So we have shown that when doing the subgraph matching, we only need to look into a very small, reduced search space in the quantum hardware. That means we don't need to search over the entire quantum hardware and see which part can be used to implement our quantum circuit. We only need to focus on a small part of the quantum hardware and find all the group of qubits there that can be used to implement our quantum circuit. And this, and here we have demonstrated a theorem that back up this idea. So this theorem is based on the definition of generating set. So the generating set is a mathematical description of the so-called repeated pattern in a graph. So in the language of physics, let's say we have a lattice with some spatial periodicity, right? Then we have a unit cell that can be used to cover this entire lattice under translation operation, right? And this unit cell can be abstract to this concept of generating set. So that is the idea of generating set. So we have shown that if we know we have a graph with some symmetries, then it will have a generating set correspondingly. Then we only need to search over a region neighboring to this generating set for all the subgraphs isomorphic to a certain pattern. So this is how our circuit subgraph matching based on symmetry works. So, and we have proposed an algorithm based on this based on our theory. So this algorithm will not search over all the pattern graphs that we are interested in over the entire quantum hardware. Instead, it only searches over a neighborhood of the generating set, which greatly reduces the computing load. And based on this subgraph matching algorithm, we can efficiently look for the optimal circuit remapping. And what's interesting is that we have shown that in many practical cases, our algorithm, based on the symmetries of quantum hardware, has a time complexity that scales linearly with the number of qubits in the hardware. And this turns out to be optimal for the subgraph matching problem, and of course, therefore, the circuit remapping problem. Benchmark results have been presented here to compare the efficiency of our algorithm and the previous subgraph matching algorithm and the circuit remapping algorithms. So our subgraph matching algorithm shows, you can see that the runtime of our algorithm is lower than previous traditional VF2, VF2++ subgraph matching algorithm by, I think, 1 or 2 orders of magnitude. And our circuit mapping algorithm inherits this speed up. That means compared to a previous circuit remapping algorithm, mathematic, our algorithm also shows a reduction in runtime by 1 order of magnitude. Very efficient, which also aligns with our proof of the algorithm's optimality. In summary, so my talk contains the following messages. First, there are significant fluctuations in gate error and measurement error across existing quantum computing systems. And these fluctuations make it important to implement our quantum circuit only using the high quality qubits and gates, right? And in order to achieve this, there is a recently proposed method known as quantum circuit remapping. However, the previous implementation of quantum circuit remapping has a high computing load. And our contribution is that we have shown that by using symmetries in a quantum hardware, we can significantly speed up quantum circuit remapping process. And our algorithm in many cases have been shown to be optimal in terms of time complexity. And and this is all of my talk today, and I hope you enjoy it. So any question?
Thank you for the talk. Is there any question? Oh, can you hear me now?
It seems something is wrong with. Okay.
Okay, so I need to
Please go ahead.
ask in chat.
Okay. That's the end of my part.
So sorry, I have a question. Could you show me the your slide again?
Yeah, of course. So which slide you are interested in?
So I could not get the message of your talk. So
Message.
yes, you are mainly considering the not compiling. So previous talk discussed the compiling, but your talk mainly considering some noise protection.
So the main message of my talk is that we present an algorithm that is highly efficient for solving subgraph matching problem if given symmetries in given symmetries of the graph. And our subgraph matching algorithm results in a very efficient circuit remapping algorithm, which proves to be optimal.
So I could not understand so much. Could you show me the problem again? Your
Sure.
problem. So this is algorithm. So firstly, you need to show your algorithm, your problem. What problem to be solved?
You mean problem?
Yes, problem. What problem?
Hmm.
This problem.
Yes, subgraph matching problem here.
Huh? わからんな。え So quite difficult to understand. Uh, Once you have we are given one graph. So this
Yes,
one is
yes.
V and E, and what is the solution? What we need to do for this graph? Given graph, what are all subgraph in G that are isomorphic to? There is two graph G and T.
Yes,
And
yes, yes.
we need to list up all subgraph such that they are equivalent to T.
Yes, yes.
Yeah, you can imagine that G is very large graph and T is small, and you can find some parts of G looks
yeah,
like
yeah. Exactly. So the graph G is a large graph that represents qubit connectivity in a quantum hardware, and graph T represents the required qubit connectivity by the quantum circuit that we want to implement. So we need to embed the graph T into graph G if we want to implement our quantum circuit using quantum hardware.
So then, what is the, so I could not understand. This one is still quite difficult, classical one. So you get some algorithm, and that algorithm truly faster than classical one, or this is only numerical one. So what one is in many cases complexity ON. But this is quantum one. But how about the existing classical case?
Maybe my audio doesn't work very well. So
I cannot. Could you show me the what is existing result for classical case for that problem? Classical case.
Oh, this is also classical algorithm, right?
You propose classical algorithm.
Yeah,
Not
yeah, yeah.
Yes, it's indeed a classical. It simply find the graph isographs in the large graph. So classical algorithm, if you do not make use of the symmetry, will be given by what is the df plus, right? So the complexity is roughly like two at least n to the power of 2 if you do not use symmetry.
So I cannot understand. So then this one improve classical case or no?
Yes, you can say that.
But I could not find how much improve. So classical
Yes,
case, complexity ON, and quantum case also ON. I don't know. But some coefficient can be improved.
Mm,
なんでこんなちゃんと答えれないんだ。
what is the yes? It's better to have a look at the paper, so we have discussed this. So the classical algorithm is called VF2. It's a very standard algorithm for found the isomorphic graph. And the complexity for this one is at least polynomial. But here we make use of the symmetry of the graph. So the complexity can be reduced to linear.
Linear.
Yes.
What polynomial? So no exact order.
It's very hard to analyze the classical algorithm, the complexity of the classical algorithm
Okay.
precisely.
Okay, I understand. But you need to make that kind of comparison. Otherwise, people could not understand the advantage of your.
Yes. Yes, we did this in the paper, but yeah, it's better to introduce it here as well. Yes. But the key message for this work is that we have symmetries in quantum chips, right? And this will help us to reduce the problem a lot.
Okay, I understand.
so if there is no further question, I think I will stop sharing my screen.
Okay.
So it's time, so let's thank the speaker again. Next talk will start in 5 minutes.
ね。
聞こえますか？はい。
テストです。はい。
OK、OK。うん。うん。
はい、先生、業務連絡ですけど、こちらの次の次のスピーカーの方がまだ現れてないので、もしかしたら多少遅れるかもしれないです。
どちらの人だっけ？どちらって。ごめんなさい。私覚えてない。
シュウ・デュオさん。
ああ、だから西村さんの学生ね。
名古屋大学の。はい。
そうなんもんやな。ちょっといろいろとあるんだよな、なんか。
では、時間なので始めます。So it's time. Let's start next session. So the next speaker is Shintaro Minagawa from Nagoya University, and he is talking about operational approach to information and thermodynamics. Please start.
Thank you very much for the introduction, and thank you very much for inviting me to this workshop. Yeah, I would like to talk about. I'm Shintaro Minagawa from Nagoya University, and yeah, I would like to talk about the operational approach to information and thermodynamics. And yeah, this is the abstract of my uh, talk. So the basic question is that why is the nature where we live now described by quantum theory? And yeah, there are maybe several approaches to this very fundamental question. But yeah, I would like to approach to this problem from the thermodynamics and the information theory, and yeah, especially operational viewpoints. And yeah, so yeah, thermodynamics part is the second law of thermodynamics, and the information theory part is we consider information transmission in operational framework. And these are the corresponding papers of this talk. And yeah, I'd like to thank the co-authors who teach me always a lot. Okay, so yeah, first I'd like to briefly talk about some axioms of quantum theory. Yeah, quantum. So yeah, they are not all, but yeah. So many people say that yeah, quantum systems have a complex Hilbert space, and also yeah, quantum states are density operators, and quantum measurements are described by POVM, and yeah, composite systems have a tensor product Hilbert space, but yeah, there are some question because yeah, why complex Hilbert space? So why Hilbert space, and also why the field is complex? And also, yeah, why this kind of Born rule or probability of obtaining? So yeah, why we can calculate the probability of obtaining the measurement outcome like this one? And also, yeah, so this question correspond to the why do entangled states exist? Yeah, because we can consider the quantum we can consider the theory where only the separable state exists. So yeah, there are the question to these axioms. Yeah, of course, we can admit these axioms, and yeah, we can calculate and also predict the experiment results. But yeah, why is the nature where we live now described by quantum theory is the summarizing of these questions. Yeah, the summarization of these questions. There are maybe several approaches to this problem, but general probabilistic theories is one of the most well-known approaches to this problem. So what is general probabilistic theories? In short, GPTs. So we consider so in general probabilistic theories, state law and measurement are somehow determined, and then we can calculate the probability of obtaining the measurement outcome k. So there are rules to calculate a probability of outcome k is determined. So this kind of operational viewpoint of theories can be mathematically described by using finite dimension. So here, technically, we assume the finite dimension, but some people consider infinite case. So yeah, so this kind of operational viewpoint can be mathematically described by using a real vector space V with an inner product. And also, so there is an inner product, so we can consider dual space V, dual space of V, which is V star. And we can consider positive convex cone, which is a subset of V. And yeah, so positive means that for all x in K, then by taking lambda x, so lambda is non-negative value, and it is still in K. And also, the convex means that for all x1 and x2 in K, then if you take a convex mixture, then it is still in K. Then we can define a dual cone K star, which is a subset of V star, defined as this one. So for all x in K, and then by taking inner product with y and x, then it is non-negative. So K consists of such a y. Then we fix a unit effect U in K star, and we can define state, which is a element of K, such that if we take an inner product with U, then it is equal to 1. And measurement consists of a family of effects, and taking a summation over all measurement outcome I, then it becomes a unit effect. So we can consider the framework to calculate the probability of obtaining the measurement outcome I. So yeah, just taking inner product with measurement effect EI and quantum so the state law. Yeah, we can confirm that EI law, the inner product with EI and law is non-negative. And if we take the summation over all measurement outcomes, then it becomes 1. So it satisfies the axiom of probability. So the motivation of GPT is like this one. So yeah, what operational properties characterize quantum theory? And yeah, is there any theorem universally valid in GPTs, not only in quantum theory? So by answering these questions, we can understand what quantum theory is more deeply. So yeah, because it is known that GPTs includes not only quantum theory and classical theory, but yeah, many other theories. So yeah, what characterizes quantum theory? And also, yeah, we know some theorems in quantum theory, but so we can consider its generalization to GPT. So yeah, by understanding them, we can understand quantum theory more deeply. Okay, so I would like to go to the entropy part. And yeah, before proceeding, I would like to explain the quantum entropy. So yeah, this is well known, quantum entropy or von Neumann entropy. This formula is given by von Neumann. And yeah, there are some alternative definitions or some classification of von Neumann entropy like them. So one is that, so by taking, so first we take rank 1 POVM. Rank 1 POVM means that any elements of POVM consists of rank 1 operators. And then we calculate the Shannon entropy of the probability distribution of that rank 1 operator, rank 1 POVM, and then taking a minimization of that Shannon entropy. This is also equal to the von Neumann entropy. And another definition is like this one. So first we decompose, so we can decompose the mixed state into pure state because state space consists of a convex, state space is a convex set. So yeah, we can decompose into extremal points or pure state. So but there are several decompositions basically generally. So then we minimize that so Shannon entropy of the decomposition coefficient for all decomposition into pure states. So it is also equal to the Shannon entropy, von Neumann entropy. So yeah, these alternative definitions of von Neumann entropies can be straightforwardly extended to GPTs. So these three papers are considered that extensions in GPTs. And the first one is called measurement entropy. So minimizing the probability, Shannon entropy of the probability of obtaining the measurement outcome. So with respect to fine-grained measurement. So in quantum theory, fine-grained measurement is rank 1, but fine-grained means that that measurement cannot be created by coarse graining. So yeah, just opposite of the coarse grain, fine-grained. So another one is that, yeah, mixing or decomposition entropy. So yeah, this is a state space, and this is some mixed state. And then we can decompose it into pure state. And this is a probability distribution. So we can calculate the Shannon entropy, and then minimizing over all convex decomposition into pure states. Yeah, we can. So we can define such an entropy in GPTs generally, but it is known that in some GPTs, measurement entropy and mixing entropy is not equal. But in quantum theory, they are equal, and it is equal to von Neumann entropy. So coincidence of entropy looks like a very important properties in quantum theory. Okay, other entropy is spectral entropy defined by this paper. So first we define the notion of perfectly distinguishable states. A family of states are perfectly distinguishable if there is a measurement such that if we take inner product, then inner product with EJ and Y, then it is Kronecker delta. Then the mixed state decomposition is said to be spectral decomposition of rho if rho I are perfectly distinguishable pure state. Then we can calculate a spectral entropy as a Shannon entropy of this decomposition coefficient. So yeah, in quantum theory, any state has an eigenvalue decomposition like this one, and yeah, phi I are perfectly distinguishable or orthogonal in quantum theory. And this in this decomposition, yeah, pi is uniquely determined, and then yeah, spectral entropy is also unique, and it is equal to von Neumann entropy. Okay, so now I'd like to explain our main, so one of our results. very briefly. So in some GPTs, we can consider some GPTs like one state has multiple spectral decompositions, and also the channel entropy are different. So yeah, this is a different spectral decomposition, and the HPI and the HQG are not equal. So in this case, how to determine spectral entropy in GPTs become problems. But our work shows that under the second law, and yeah, some operational assumptions, but basically under the second law, then we can define the spectral entropy uniquely. So the take-home message is that it is the second law, not the spectral theorem, to make entropy unique. So this is one of the results, and I'd like to proceed the next part of my talk. So we in another paper we consider the classical capacity in GPTs, and we consider the relationship between the classical capacity and the hypothesis testing. So I would like to explain the hypothesis testing and also its relative entropy in GPTs. So this is a setup. So this is a machine that produces state rho or sigma. Yeah, we know so this machine produces rho or sigma, but yeah, at that time, so we do not know which one, but yeah, we know rho or sigma. Okay, so then there are two types of errors. So one is that this machine produces rho, but this person considers that this state as sigma. And this is type 1 error. And another error is type 2 error. So this machine produces sigma, but this person considers this state as rho. Yeah, this setup can be modeled as this kind of so two outcomes measurement. So E consists of effect E and another effect U minus E. So E corresponds to rho and U minus E corresponds to sigma. Then, yeah, type 1 error probability can be calculated as this one, and type 2 error probability can be calculated by this one. Then the hypothesis testing relative entropy in GPTs is defined as this one. So the meaning is like this. So we would like to minimize the type 2 error under the constraint that type 1 error is under epsilon. In quantum theory, this is firstly introduced by this paper, but we consider, so we can completely operationally define the hypothesis testing relative entropy in GPT. So we use this one. Then I would like to consider the classical capacity in GPTs. So the setup is like this one. So sender A prepares some messages. So messages is in n-length binary sequences. So there are 2 power n messages. Then it would be sent to encoder G. G is a map from gamma to some alphabet. So yeah, this is a correspondence. And the channel here is a map from alphabet to state of some convex, positive convex cone K. Yeah, this is a correspondence. And finally, the receiver decodes and obtains the message J prime. So this is a measurement. So is a measurement which is a map from the state to alphabet. Then, so yeah, the setup consists of the encoder and decoder and channel. So 2 power n epsilon code consists of an encoder and decoder satisfying that averaged error probability of all messages is under epsilon. Okay, so and also, yeah, the non-negative value R is an epsilon achievable rate if there is a 2 power R epsilon code. Then one-shot epsilon classical capacity is a sublimum of R, where R is epsilon achievable rate. Okay, so it is known that in quantum theory, epsilon classical capacity is evaluated by using a hypothesis testing relative entropy by this paper. But yeah, in our result, we showed that the similar inequality in any GPT. So in any GPTs, we have this inequality. So this is the classical capacity. So we have a upper bound of the classical capacity and also the lower bound. So And yeah, here pi ABPX is a state like this one. So this is a classical GPT state which can be prepared by the channel we consider. And yeah, this was a one-shot case, but moreover, yeah, hypothesis testing and classical capacity are asymptotically equivalent in GPT. So this is an asymptotic classical capacity, and yeah, which is equal to this kind of, so the hypothesis testing relative entropy. So yeah, to show this, we use the left continuity of this hypothesis testing relative entropy with respect to epsilon. Okay. Okay, so I'd like to conclude my talk. There are several definitions of entropy which are not equal in general. But when we consider the second law of thermodynamics, then it makes the spectral entropy unique. So otherwise, we can violate the second law of thermodynamics. So such a theory is very weird for our nature. So then, okay, so there are several open problems. So we consider that the second law of thermodynamics and the uniqueness of spectral entropy, but so the some big open problems is how the second law so restrict the mathematical structure of physical theory. So this is one of the important problems. And also, yeah, we only consider the second law, but we can so there are a lot of other physical laws like first law and third law and yeah, many other physical laws. So how that physical laws restricts the mathematical structure is also one of the important problems, I think. And another paper is that, yeah, hypothesis testing relative entropy is closely related to the classical capacity. And yeah, its relationship is not only in quantum theory, but also universal relationship. So this is the end of my talk. Thank you very much.
Thank you for the talk. Is there any question?
Could you show me the relation between the hypothesis testing and the channel capacity?
Yes. Yes. Okay. This one?
Personally, I have to say that the contribution of one Leonard paper is quite small. They have almost no technical contribution. Their contribution is introducing the concept of the hypothesis entropy. Only this one. All technical result comes from our paper with Nagaoka, my paper with Nagaoka.
I see.
They always cite, they clearly cite my result. So there is no technical result. Technical result is come from our paper.
Okay, I understand. Yeah. So basically, we should say that we generalize not this paper, but your papers.
Of course, our paper did not mention that the hypothesis testing entropy, but the relationship between the channel capacity and hypothesis testing already stated. And we present so many things by using the terminology of the information spectrum.
Mm-hmm.
So clearly, we said that there is several remarks, and we said that kind of relationship. But at that time, we did not write down the concept of hypothesis testing relative entropy. But of course, we always consider that the minimum of the hypothesis testing, we consider that quantity, we usually write down this beta epsilon. So beta epsilon already introduced. But we do not take that logarithm. So then he introduced hypothesis testing entropy. So
Okay, so
yeah,
yeah,
difference, small difference, technical terms or something. So one Leonard paper almost has no technical contribution.
I did not know that. Sorry for, and yeah, thank you very much for.
No, but if you clearly read their paper, you can easily find they cite our paper. So.
Okay, I understand. So yeah, I will carefully read that. Yeah, paper. Yeah, thank you.
Any other question? If not, let's thank the
So
speaker.
please, wait. Yeah.
Oh.
Could you show me again the next slide? So then you proved this.
So yeah, in our paper, we proved this. So yeah, in one shot case, this inequality, so there are some this term, and yeah, but yeah, we use the continuity of the hypothesis testing relative entropy with respect to error probabilities, and yeah, we show this equality. Yeah.
No, but this is somehow confusing. So how did you consider n-tensor product case?
Yeah, so in quantum case, yeah, that would be okay. But in GPTs, yeah, so we consider the, so in our paper, we explain that, yeah, there are no determined composite systems in GPT. So yeah, but this, so how to say, so this is, so the left-hand side also, depends on the structure of the composite system of GPTs, and the right-hand side is also. So then, yeah, it is just how to say, so the relationship which is valid for any composite systems of GPTs.
But this is essentially come from the classical information spectrum. So this is only the corollary of the classical information spectrum, I think.
I see. Okay, so yeah, actually, yeah, this is a classical to quantum capacity. So yeah, classical part would be also, yeah, correspond to, yeah, I'm not sure, but yes, thank you for the suggestion.
Because in that situation, you should choose some optimum choice of the measurement. So then,
Yes.
once we have some choice of a measurement, we have a sequence of classical case. So then you can simply apply existing classical result.
I see. Okay, so yeah, actually, so in our paper, so the proof is not to depend on the composite systems of GPT. So maybe only the classical things would be used, I guess. So yeah, but I did not know. I did not realize that. So yeah, thank you very much for your comments.
Okay, so it's time. Let's thank the speaker again.
Thank you very much.
Shu-san, could you share the slide?
Yes. Oh, okay.
Thank you. We can see.
Can everyone see the screen now? Okay.
So the next speaker is Duo from Nagoya University, and he's going to talk about how to certify derivation with constant length key. Please start the talk.
Thank you. Thank you for the introduction. Hello, everyone. I'm Shuto from Nagoya University. Today, I will talk about how to certify dilation with constant length key. To begin with, in this slide, I will introduce the motivation to consider certified dilation. Nowadays, cloud storage is very popular, right? It allows a client with limited storage to store large encrypted files on some servers. It is natural to think about how to delete some files from the server as well. It may save some storage, right? Classically, this can be simulated by simply ignoring the file that the client wants to delete. It will be protected by the encryption after a long time. But a hidden risk is that the server may keep the encrypted file and apply some retroactive attacks, which are shown here. Certified deletion resolves this concern about the retroactive attack. And let us go to the next page. Certified deletion is as follows. The sender sends a ciphertext consists of quantum states to the receiver. At some point, the sender can issue a delete command. After receiving the delete command, an honest receiver is able to produce a valid certificate, while a malicious one cannot forge a valid certificate without destroying the actual ciphertext. The protocol is computationally secure during the execution. But after the deletion and the certificate is valid, no information processing process can recover the plain text. For a wide range of protocols, such as bit commitment, zero-knowledge proof, and the public key encryption, the certified deletion is implemented. So it is quite a mature technique to implement some certified deletion. So far, certified deletion solves the problem of retroactive attacks perfectly. However, all the prior works require the verification key to grow with the size of the message. It is like to certify the deletion of a 1 megabytes file. We need to keep a list of keys that is as large as the original file. But wait a minute. If the client has the storage to store that very long key, then why not store the file instead? That's a problem. This leads to a contradiction in the motivation. And to solve this problem, we propose the method to reduce the certification key to constant length. It means for polynomial sized file, the key does not grow with the file size. This slide shows our contributions. Our contributions consist of two parts. One is a new general lemma. We proposed a new general lemma with which the verification key is only order lambda bits. It can be used to construct bit commitment, public key encryption, secret key encryption, attribute-based encryption with certified deletion, and revocable timed release encryption. Also, we see that the prior works focus on weakening the computational assumption and extending the notion of certified deletion to more primitives. We believe that the reduction of the key can be a new trend for certified deletion. In this table, we compare our work to the prior works. This is almost the original work which produced a general lemma about the certified deletion. It requires the private key to be at least order lambda n bits. Well, this one adapts the verification key to be public key. It also requires order lambda n bits of the verification key. Our work reduced to only order lambda. For the notion appears in the table we explained here. Next, we will demonstrate our method using an encryption scheme. Before the demonstration, we will introduce something called the pseudo-random functions. Pseudo-random functions are a set of functions that are indistinguishable from random functions for a polynomial time adversary. It is like if the adversary can query a function through some oracles, it cannot distinguish whether the oracle is a truly random function or a pseudo-random function. And let's begin with the scheme itself. The key generation first fix a set of pseudo-random functions gk. The k is the key of the pseudo-random functions, and the simple random seed k. This k is the verification key, and it will be used in both encryption and verification. In the encryption part, in the encryption phase, first use the key k to calculate many pseudo-random strings. These strings all looks like independently random strings if someone do not know the verification key k. And to encrypt every bit, we will prepare this kind of states as a ciphertext. The value of that bit is encoded in the phase. And to delete, to produce a valid certificate, the receiver measures the ciphertext in computational basis, and the measurement outcome is a valid certificate. Since the sender has the verification key k, he can calculate the two possibilities of a valid certificate by himself. It is namely the xi0 and xi1. And he checks whether the measurement outcome is one of the two possibilities. Next, I will explain the building blocks of our method informally. Our work base the computational security on the secure harness to detect the face. And it said that for this kind of two states cannot distinguished if and only if there's a unitary which swaps the two states, which is the black state and the white state. And we will see this kind of special systems is utilized in our method. The special system is constructed by first simple two random string x0 and x1, and then simple a random bit b, which is 0 or 1, and prepare the state in register R. No algorithm taking register R as input can guess B with an unnegligible probability larger than 1/2. This is because for two random strings, one cannot construct a unitary which swaps the two values. It is information theoretically impossible. And to decrypt the phase, one can construct a unitary as follows. It is simply a Boolean function. which just swaps x0 and x1. And apply an Adman test, the phase can be read out with probability 1. So our ciphertext remains hidden if someone do not know K and cannot compute x0 exclusive or x1. Second, we use the pseudo-random instead of true randomness. This makes the verification key very, very short, actually almost constant. It is simple. Recall the special system described before. We just replace his part, simple two random string x0 and x1 by compute to pseudo-random string x0, x1 with gk. Since a GPT, a quantum polynomial time adversary, cannot distinguish between random and pseudo-random functions, our protocol remains computationally secure. And also described before, the sender can compute x0 and x1 from K. So it can just use the key K to verify every bit's deletion. And why do we say that the bit is deleted? It is because actually there's no other way to produce a valid certificate than measure the ciphertext in computational basis. And after a computational basis measurement, the phase just disappear. Also, I would like to talk about the future research in the future. It is towards an ideal certified deletion. So far, I think an ideal certified deletion should use the public key to verify the certificate, and it should remains the constant key length. And I would be thankful if anyone can point out what other aspect can we improve about the certified deletion protocol. Actually, there's an ongoing work which implemented a certified deletion with constant key length and public verification. And it is thanks to a reviewer of the conference ICIT 2024. And this is the conclusion. We proposed a new general lemma for private key certified deletion. And the general lemma reduced the verification key to constant length. Also, we point out that the reduction of verification key is a new research direction about the certified deletion. Here's the reference. Our method mainly improved their work only from the length of the verification key. Also, I would like to take the place to thank the CERS Make New Standards program for the next generation researchers. Thank you very much.
Thank you for the talk.
Mm.
Is there any question?
So, sorry, could you show me the problem setting again? What problem you are solving?
So, what problem did I solve? That's the question, right?
Yeah.
I actually reduced the length of the certification key. And so now we do not need to store a very long verification key locally. It reduces the cost of storage and reduces the hardness of key management.
Wait. Still, I could not understand. So, you want to reduce something, but maybe there is some original problem. So, what is original problem? So, you want to reduce the key cost. So what is problem? So, you need some, you want to consider verification key. I cannot understand length of key, certify. So, what's the purpose of that key?
I beg your pardon, the last phrase, I didn't.
I could not find the purpose of that key. Purpose. So why you need to consider key?
It is because well, this is very interesting. It may be possible that we do not need a certification key at all, but I don't think it's very possible.
No, I
And
understand. So what is the role of that key?
okay, I understand. The key is used to verify whether the certificate is valid. So if the certificate is valid, then the original information is completely disappeared. But if it is not it is invalid, then it is not information theoretically deleted. And we need the key to check whether the receiver, well, did the deletion process honestly.
I cannot understand the deletion process. Usually, in that case, why this is cipher text? Because in that case, there is a text message and there is some key holder, and using that key, they made some signature. So,
Yes.
authentication problem. This is authentication problem.
Actually, for the encryption, it just makes the encryption very hard to use. But for the bit commitment, which consists of two phases. One is the commitment phase and one is the reveal phase. In the commitment phase, the sender wants to hide the information from the receiver, and the certified deletion enables the sender to ask the receiver to abort the protocol. And actually, this kind of nature can be utilized in the zero knowledge proof to achieve some security called everlasting certified security. This just prevents retroactive attack.
So sorry, I cannot understand. You are considering bit commitment, not message authentication. So because you have some certificate, usually certificate used for the message authentication, but this is not message authentication. You are considering bit commitment.
The certificate is used to prove that the receiver actually deleted the information underneath. So it is not some signature about the plain text itself. It is a certificate about the disappearance of the information.
Disappearance for information. I can't understand. Disappearance. What is this?
Yes, this certificate, if the certificate is valid, then the ciphertext is deleted and no information processing process can recover the plain text. It means, well, this is itself is actually not achievable.
Is valid. So then no information recovered. If the certification is invalid, so then I could not understand purpose of the Dutch protocol. This is quite complicated. Oh.
Well,
this is certificate deletion. So
yes,
certificate deletion means
that one can check whether the receiver deletes the information. It is like if I can send you some information, well, via email or something else, and it classically, if I ask you to delete the email, I cannot check it because you can keep the email secretly, take a copy of, and so the classical deletion is not certified.
You obtain some message, so then if my memory is very nice, even though I remove that message, so still I could memorize everything. So then that kind of certificate does not make sense.
Actually, this is the point. To apply a encryption with certified deletion, one cannot send the decryption key in advance. One must keep the decryption key, well, locally. This seems a drawback for the encryption, and this is right. So to make the certified deletion work, the information itself must be kept computationally secure before the deletion. And this sounds not useful, right? But for commitment or the revocable timed release encryption, this is exactly the situation where in this kind of protocols, the information itself is hidden until some point.
Information should be hidden because this is ciphertext.
Yes.
Then if the okay, I understand. If that person could do not decode that ciphertext, then this guy can send the certificate.
Yes. Well, this is a very good question about about a basic contradiction in the early period of certified deletion.
Of course, this ciphertext written as a quantum state, you cannot copy. So maybe we can make some certificate. But in the case of classical one, this one does not make sense. Still, that person can memorize that kind of ciphertext.
Yes, so the receiver must so the sender must ensure the receiver cannot decrypt the ciphertext until he decides whether he should send the decryption key or should ask the receiver to delete. Yes. Thank you very much. Any questions?
Seems it's time, so let's thank the speaker again. And the next session will start from 2:30 in GST and 1:30 in CST.
And please announce that program change. But already people gone.
Yes, the schedule has been changed. So the first speaker of the second session is canceled. So we move the last speaker to the first session. The conference end in like 3:40 in JST and 2:40 in CST. Thank you.